My name is Kensho Tsurusaki from the University of Tokyo, and yeah, thanks for inviting me here. And so first, I apologize for being late, and you can guess I was preparing the presentation, so it may be somewhat low quality, but I did the presentation, and this is the outline of my presentation. First, I introduce my proof of concept implementation of doing literate programming in Lean version 3. And next, this is not my work, but I will introduce an interesting previous work using Lean 4's metaprogramming feature to design a controlled natural language in Lean. And then I talk about my ongoing work of improving my current implementation, including its migration to Lean 4 and adding new features. It's not maybe unnecessary background, but we have two types of proof, formal and informal proof. And formal proof is written with formal languages, like programming languages, and it's verifiable by theorem provers. And language includes Coq, Isabelle, and Lean. And in this context, we call the traditional proof in natural language as a informal proof. But formal proof has, some disadvantages. In Word, it looks completely different from the informal proof. First, it tends to become very long and redundant compared to the informal proof in order to include every inference step to convince the computers to the correctness of proof. And also, reading and writing formal proofs requires some expertise relating to the syntax or semantics of each formal language. Then I compare three approaches of mixing formal and natural language. Maybe this is very suitable for the previous workshop, maybe, but so these are three, roughly, it's my categorization, but definitely there are three types of mixing formal and natural language, I think. And one is controlled natural language, and it is defined by restricting some vocabularies of natural language, and it's still a formal language. So it's based on the formal structure, is the controlled natural language. And the next approach is flexiformal approach, and this is writing some content by formal language and other content by natural language. And the last approach is literate programming, and this is providing both formal and natural language for same content. So explaining the same content twice is the literate programming. Now we look into each approach. And controlled natural language is like this, and this is a kind of bad example. So the characteristics of controlled natural language, important characteristic is it's based on formal structure. So it's kind of putting natural language component onto the formal structure. So it's still bounded on the formal structure. So, for example, it may contain some repetitive or unnatural sentences, or this is not so bad, but it's a bit redundant than just writing k equals p comma 1. And so the good thing about control natural language is it has 100% verifiability, but one thing is it looks like some kind of literal translation of formal language and less readable for human. The next is the flexiformal method, and sorry, ignore the first line. Sorry, it's wrong. And second line is also sorry. And yeah, this is the step, typical or only implementation of flexiformal method, and it's rendered as like this. So this is completely readable because it allows using every natural language component. So the good thing is 100% readability, but bad thing is it's not fully formalized. So some parts are only explained by natural languages. So it's not verified as on the whole. So it doesn't support the theorem proving feature currently. And this is the last research programming approach. And literate programming is a kind of using natural language along with formal language. So then we are neither bounded by natural language structure nor formal language structure. These two lines are correct. Sorry. Yeah. So flexiformal language is bounded on natural language, and so control natural language is bounded on some formal structure, and so literate programming is neither. So yeah, and literate programming is originally proposed by the Knuth, who is the developer of the PEG system, and its original meaning is maybe a bit different, but basically it's writing natural language and formal language in parallel. And the good thing is, so we have both 100% readability and verifiability because we write both of the natural language and formal language. But the good thing is there is no explicit correspondence between such comments and formal contents. So we can basically write everything in comment, so it may be not related to the formal programs. That's a problem. So it's my approach, my implementation, called NTAC, but the name is not important. And this is a library that enables literate programming in Lean, and currently I'm migrating it to Lean 4, but this slide uses Lean 3 version, and the Lean 3 version is at here. And in this system, we can attach any natural language text on the tactic block to explain the contents of tactic block. Then we have explicit correspondence between proof procedure and the attached comment, and then it can be converted into an HTML document, and such a generation of document is an essential feature of literate programming. And the HTML document have some rich interface that is separated into outline and detail area, and it's suitable for longer proofs, and I'll show them afterwards. And also, math expressions are pretty printed by Patek. It's converted to from Lean expression, and actually this feature is automatic conversion of some tactics into natural language text, but currently the implementation is very limited, and I don't think this feature is so cool, but yeah, it still has the feature. So firstly, so then I looked into its implementation further deeply, and this is a toy proof written in Lean, proving P and Q from the separate proof of P and Q. And this slide contains animation. So we have first the initial goal, only one goal, and then we use split tactic to split the original goal into two separate goals, each for P and Q, and yeah, so then we have two goals, so P and Q, and then we solve this by using the proof of P, HP, to solve the first goal, and then proof completed. And so we can conceptually has a tree structure like this. This is that explains how each codes are converted and resolved. And actually, the bottom line explains the implementation detail. So I modified the original tactic monad in the Lean 3 to contain this tree information as an additional state. So the existing Lean implementation has only the current status as the monad state, but I also added the history of execution into the monad state, so we can get the tree structure after the execution of proof is completed. And this is the basic feature of this is basic explanation on how Lean works. But this is my modification on the literate programming thing. So yeah, again, the name is not important, but for example, this is a tactic for attaching a comment onto the existing proof, existing tactic log. So this is the code, and this is the proof is semantically completely the same for as the previous one, but again this time these two tactics are respectively attached these comments by my tactics. So this tactic firstly executes the tactic as is, and then relates the given comment onto the tactic block. So then we have. So this is the previous the tree structure that is obtained from the previous example. But if we use literate tactic like this, we have this tree structure instead. So natural language comment is attached. And the important point is this is expression. So P, Q, and HP has each meaning in this Lean code. So they are written explicitly, so separated from the comment, and then Lean can type check if they are correct expressions. So, for example, we cannot write here as A or B, such an unknown identifiers, or P plus Q, which is adding the logical value, so which is not type correct. So yeah, and so then we can do anything with the obtained tree structure. For example, generating HTML output. And this is the.
What the TTT in the previous line?
Sorry. Yeah. Basically, you can ignore it. This is actually the first one is deciding if we parse these expressions before the execution of this tactic or after execution of this tactic, and the second TT is so basically these are true or false. So true or false variant. So these are both true, and so the first one is as explained, and the second one is decides the more. It's not less important, so it's only relates the output form. So you can ignore this. And yeah, so as I explained, the generated HTML has two areas: outline and detail. And when a comment is attached to a tactic block, so the comment will be placed in the outline area, and the surrounded tactic will be placed in the corresponding detail area. And this tactic is not surrounded by comment, as you can see here. So this will be auto-translated. So I'll show the demo of the first limit first. Yeah, this is the.
Is it possible to change the theme from black to white, maybe?
Okay. Yeah, so yeah, this is the proof I explained just now. So the first sorry, there maybe is yeah, so this is the sample code and this is the output. And so you can see that each comments are written in the this outline area, and we can hover mouse on the outline area to show the corresponding detail. And this is the auto conversion of exact tactic, which is surrounded in natural language comment. And I can show a bit larger. Sorry. So the next example is relating to the proof of the formula generating the Pythagorean triples, which I found moderate example for testing my library. And this is the output and this is the code. So the comment is converted into the HTML output, and so if we write some illegal thing here, so it will show the type error here, and yeah, so since the so the output should be response in real time with the updation of this code, but due to the specification of the VS Code extensions, it's not so. There are some latency in here, but basically we can just rewrite some code to get the different outputs. So, for example, I rewrite here to Z, and then we get that slash that here. So yeah, like this. Yeah, and so yeah, as you can see, this is the Lean 3 code, and Lean 3 has a kind of metaprogramming feature, but it's still weak compared to Lean 4. So we only have this a bit awkward syntax separating the comments and the syntax with comma in listing, but I have a new implementation in Lean 4, which has a much stronger macro feature to allow more extensive grammar. So yeah, this is my Lean 4 implementation, and so this is incomplete, and I don't have. I don't have result now, but yeah, this is the updated. I have result. So this is the result. Oh, yeah. So yeah, this is the comment. Dot focus. So these three are literate tactics, and we have comment shown in here, and so as you can see, we can write this bracket to insert the expression into the code, into the comment, and of course we can have.
Just wait till it comes back.
Yeah.
Sometimes.
Yeah, not touching that. Okay.
And tweak the
The
cable.
hand one.
Yeah, I probably need to reattach the, like pull it out and put it back.
Okay. So yeah, so we can of course update here to test the type checkers. So this is a type error. So
You write greater equals instead of less equal? Like if you write something that's type correct. Like what if you wrote greater equals?
greater equals, yeah, that's still passes. So yeah, this type checking is so only type checking. So checking the expression itself. So basically, we can write any type correct expressions here. So yeah, that is the future work maybe. But so. Yeah, so that is the part of introducing my work, and this is the yeah, this is the introduction of a related work that I found interesting. And this is by Gordon and Matkiewicz, called Trustworthy Formal Natural Language Specifications. And this is this work designs a control natural language in Lean 4, exploiting its strong metaprogramming feature. And this is a small example, and I'll show the demo afterwards. But for example, this is a Lean expression in this library, equivalent to this Lean expression. And in theory, it's using the CCG, combinatory categorical grammar, and which is, I'm not so familiar with this, but very close to the foundation of the grammatical framework, I think. And this is the important thing, and here we define categories in that is with a dependent type. So you can see we write type here. So for example, the letter 3, data or string 3 should have a category of NP, not. So usually we only have the NP, so category, syntax category is not dependent on types, but in these libraries it's formalized as dependent types to take a type, a semantic type as argument. And and here we have the usual definition of A/B and A'/B. And then the type class for lexicons is defined here. This is not so interesting, but so we declare a string and its category, and this is not so important. And then we give a denotation that is a meaning of the string to express a meaning of each word. So this is extracted some definitions from the library, and this contains the definitions of even and odd and two isms. And yeah, even and odd is both expressed by the Lean even and odd, and two is different in that. So first is for the adjective, and the second is for noun. So first one is a function application of adjective, and the second one is equation.
You said something about the forward slash and backward slash?
Yeah.
What do those mean?
Yeah. Actually, yeah, it's for it's in terms of the CCG, and actually, so this is A/B means that so okay, I can. So A/B means that takes B as arguments, left arguments, right arguments. So
CCG has two implications, one to the left and one to the right, and that's how we compose bits of the syntax.
Yeah. Okay, so this. So, for example, this is this expresses the term that takes an argument, left argument. So. And so we can separate these things in three components, and this is NP, and this is S/NP. So this means that take arguments in the left side, and then we have S. So yeah, basically it's function type. So function type, but so saying which direction we have that. So yeah. So and okay. And so we first defined the lexicon, and then we define the synthetic meaning, not a single word but a multiple word. So it's for multiple words, so it's a context-tree string, and it's given, it's a type defined in this library, so not so important. It's basically a list of string, and also has an denotation and string ref. This is not important again. And this is an core part of parsing. So as you can see, this is right application. So the right application and left application is currently what I explained here. So this is left application. And so these rules are all declares instances. So sorry, this slide is not okay. I will use this slide. So all definitions are declaring an instances, allowing construction of. So this allows construction of instances of synths here. No, here. Synths, and by each lexicon, which is this, and forward-backward application, which is this, and composition is these two, and any parenthesization in here. And I forgot about the shift thing, but it's type reason. Sorry. Basically, this is the most important part. So the task of searching correct CCC syntax tree was hence converted into the task of searching an instance of the synth type class. So the Lean kernel tries to compose these definitions to create the desired instance for the synth class for the given string and given sentence. So I'll show you the demo. It's a bit strange, maybe to show the demo by not me, but so okay. Use. Yeah, this is this shows that so every integer is non-negative and is non-negative is parsed as all natural numbers x is greater than or equal to 0 and greater than or equal to 0. So yeah, this is how it works. And note that the parsing is very slow because the Lean kernel tries to. So this yellow line indicates Lean is still running here. So there's several seconds to parse this because it tries to every parenthesizing to get the correct instance for the synth type class. So, but yeah, this is the demo and you can see it's working. Yeah, and this is the end of introducing the previous work, and I'll move on to the my ongoing and future work. Okay, so yeah, firstly, the most easy and important task is just migrating it to Lean4, and it's ongoing, and I think it's near completion, except the old translation feature, because it's I think I don't like it, the feature, so that may be removed in the Lean4 version, and this is the most important point. So supporting the such CNL in writing tactics. So the previously shown related work only supports CNL in statements. So it's only written as expressions, not commands. So, but we want to use natural language in proof instead of tactics. So I want to add this feature to my library. And this is also important. The previous work used Lean for parsing of the natural language, but I think we can use other external grammar parsers, including the grammatical framework or some neural-based ones. And so basically, so I don't explain in detail, but we can search which parenthesization is correct by external process, and then assign Lean meeting in each word in here. So in short, we can exclude the Ryasok definition. It is the cause of the long parsing time. So we can remove this, and so speed up the parsing. And so yeah, Lean4 metaprogramming feature is very strong, so we can call external parser during the parsing, I think. And also this is the ongoing work, So it is an idea that may succeed. So I think it's possible to use Lean expressions directly in CNL, at least in respect of Lean's metaprogramming feature. That is, so we first replace every math expressions with index the tokens like math 14 and pass it to the parser and get response with indexed tokens, and then fill each tokens back with original Lean expressions. So we can we don't need to define each expressions, but just just tokens are needed in grammatical parsers. But I think this is of course not perfect. First, the problem I already noticed is deciding the category of expressions and also constructing, also using bound variables, and also constructing an expression with from the separate expressions. So we can make these pairs. And the first is, so this is noun, and this is adjective, and that is a problem. And also we want to use a bound variable here. So we want to convert each of these respectively to this, but I don't think this is trivial. So yeah, how to determine the type or category or maybe difficult point. And also this is future work, and the most important future work and that currently I'm ignoring is evaluation. So yeah, I have to evaluate that my work works better than something, but evaluating language itself may be difficult. So evaluating some C is better than Java is maybe difficult. So, but we can. So for the CNL part, we maybe do evaluation by estimating some coverages of natural language text. Or another option is testing how much cleverer the ChatGPT begins with my structured comments. So maybe my comment will function as some instruction for ChatGPT. And also, this is far away task, but an important problem in formal proof is a single proof that for human is typically separated into multiple lemmas in 10 or 20. So that will be a problem. So we want to merge it into by some kind of inline expansion, I think, but this is a bit a sci-fi thing, I think. So yeah, this is the summary. So, hurrying up to complete this, it's a bit less informative, but firstly, I think the metaprogramming is very strong, and this should be more famous, I think. And with the literate programming and with the metaprogramming, I can develop the literate programming library, and in the library we can kind of ground each math expressions in comment onto lean, so we can explicitly write the math expressions. And so, of course, I will improve my implementation in multiple directions mentioned. So, thank you.